Hi everyone, this is going to be a short video on edge effects in parallel plate capacitors. So the idea here is that when we deal with parallel plate capacitors, we usually make the assumption that the plates behave like essentially infinite sheets of charge. Now, making that assumption will give you a good approximation for the electric field most of the way throughout the capacitor. Like as you get towards the center especially, it's a very good approximation. But when you get close to the edges of the capacitor, that assumption completely breaks down, and the expression that you get for your electric field in the capacitor doesn't really work anymore. However, it turns out that there are certain special points within the space between the plates, namely x and y in this diagram, where you can use the symmetry involved along with the principle of superposition to figure out how big the electric field at those points actually is. So while the field towards the middle of the capacitor is basically uniform, so your field lines would be evenly spaced parallel lines, I've just added these blue lines onto my diagram showing how the field lines look as you get very close to the edge. So they sort of bulge outwards. They look sort of like the field of a dipole, which makes sense considering that if you look at a capacitor on a large enough scale, it basically is a dipole, right? It's just two equal and opposite charges separated by some distance, and that causes your field lines to bend at the outside. Now, because they're bending outwards, they are less densely packed together, right? The density of field lines is less as you go towards the edge of the capacitor. And so you would expect, just by knowing that they bulge outwards like this, you would expect the field to be a little bit weaker at the edge than it is in the middle. What if you were to look at the field at the corner of the capacitor rather than just at the edge? Well, it would still bulge outwards, but now it would bulge sort of diagonally outwards, like I've shown with that orange field line that I've just added. So I've just added onto the screen here a top-down view of some of the field lines, right? So now we're looking down from the top of the capacitor. The colors on the two diagrams match up, so these field lines here are the same as these field lines here. And you can see straight from this diagram that the density of field lines is even less at the corner than it is sort of along one of the edges. So again, you'd expect the electric field at the corner of the capacitor to be even weaker than it is sort of halfway along one of the edges. So that's the basic setup for this problem. I've also just written down there a result which I'm going to quote, which I derived using Gauss's law in my last video, where the electric field of the capacitor towards the middle is Q over epsilon naught A, where Q is the charge per plate and A is the area of the plates. I've written that E is equal to E subscript I. I've just given it a subscript I to indicate that that's the sort of internal electric field. So now we're all set up and ready to actually find the electric field at points X and Y. So what you do is take your top-down view of your capacitor. You can then get another capacitor and join it so that the horizontal edges coincide to make a bigger capacitor. Now, halfway along the edge where your capacitors have joined, you have a point which is equivalent to point X on the original diagram, right? If we look halfway between the plates, that's exactly corresponds to point X on both of the capacitors, right? So then the key step in the argument is to notice that the field that you get at this point, which I've labeled X here, would just be the individual fields of the two capacitors that you've joined together, added together, right? That's just the principle of superposition. So we could write the total electric field in our sort of composite capacitor at that point as 2 times E subscript X, where EX is the thing we're trying to find. It's the electric field at point X in one individual capacitor. But then we also know that, well, now we are sort of, if you think of your capacitor as one big whole capacitor, right, by joining up these two smaller capacitors, you're now right in the middle of this larger capacitor. And so you would therefore expect the infinite sheet of charge approximation to be pretty good considering the capacitor as a whole, right, your composite capacitor. So if you add together twice your electric field at point X due to the individual capacitors, you would expect that to be equal to this EI thing up here that we previously derived by considering the capacitor to be infinite. So that means the electric field at point X is basically about half as big as it is in the center, and you conclude that EX is Q over 2 epsilon naught A. Now, one subtle point that we should also be careful to consider is the direction of the electric field vectors, right? Because as we've shown, or as I've shown with these blue field lines, they bulge outwards, and the direction of the electric field is changing as you go from the bottom plate to the top plate. However, by symmetry, at this point exactly halfway between the two plates, your field vectors should be pointing directly upwards, right? So they curve outwards here, they curve back inwards here, and so by symmetry they should be going purely vertically at that midpoint there. So that's why we can do this thing of just multiplying your individual capacitors' electric fields by 2, because the electric fields are both pointing upwards, so we just add them together. But that means it's important that point X really is directly in the middle of this dashed red line that I have in my diagram, because as soon as you go a little bit up here, for example, then your two electric field vectors from your smaller capacitors that you've added together would be pointing in different directions. And so while you could still use superposition, it would be harder because you wouldn't be able to just multiply the magnitude of the field by 2 because they're not in the same direction. In fact, we can take that argument even further and say that, well, let's say we're interested in a point up here towards the top of that dashed red line, or equivalently towards the bottom, so like along the same line, but not in the midpoint. Well, the same logic would apply that we used for the electric field at X for the vertical component of the electric field at that pink circled point there. So the vertical part of the electric field there would still be half of the electric field deep inside the capacitor, but it would also have a component in sort of along the plane of the capacitor itself, which means that the overall magnitude of the electric field would actually be stronger at the pink circle point compared with point X. I'll put a link in the description to a nice properly numerically calculated field of a parallel plate capacitor, where you can see that that is actually true, that the field at the edge is stronger up at the top and bottom than it is in the middle. So I always find it quite interesting when you can make these basic physical arguments and still get the results, the same key results that you get by doing the full numerical computation. Anyway, what about point Y? Well, you may be able to see where this is going. We're going to use a similar idea, but this time we're going to, instead of joining two capacitors together, we join 4 of them together and make a big square capacitor like this. And so then in the very center of this big composite capacitor made up of 4 small capacitors, you have a point where you've basically added 4 point Ys together, right? Because that's the corner of each of the individual capacitors. So by the same logic, you can say that 4 times the electric field at point Y of one capacitor has to again be the internal field, EI, because that's right in the center of your large capacitor. So you'd expect the infinite plane approximation to apply. And so you get that the field at point Y is Q over 4 epsilon or A, which is consistent with what we said, again, by looking at the field lines up here at the very beginning, that the field should be weakest at the corner. So that's all for this video. I always find this sort of simple physical argument stuff quite interesting, and I hope you've enjoyed it as well, and thank you for watching.